Okay, so let's look at the methods that we can use to be able to store our encryption keys, certificates, and general crypto assets. So the main method that we'll have a look at is a DER, but we'll also identify that the other core method is with the PEM format. Okay, so generally what we have is that we have a key pair. Say if we're using public key encryption, we have a private key and we have a public key. And we need some way to be able to store that key pair on a machine, and also a way that we can export the public key, and then for others such as Alice to be able to interpret that public key. So we normally have containers called digital certificates, which will contain the public key and the methods involved. And we also need to be able to store the key pair. So in terms of encryption, we might, for public key, we might be using RSA or elliptic curve. In terms of digital signatures, we might use ECDSA or good old DSA, or even EDDSA. These are different methods that are used for generating signatures. For key exchange, we might have Diffie-Hellman or elliptic curve Diffie-Hellman. So you can see that we have lots of different methods that we might be using for our encryption. So we need to find a way to define the method that we're actually using. So for example, we might be using elliptic curve, and the curve is SEPT 256K1, as would be used by Bitcoin. So with our keys, we need to store the format of the method that's used so that the keys can be interpreted correctly. Okay, so that's just some of the things that we might look at in translating keys and certificates. So the two main formats that we have are PEM and DER. DER is distinguished encoding rules, and DER is a binary method. So when Bob produces a certificate or his keys, then he can produce them in a DER format. And the DER format, when we try to list it, we will find that it's non-printable and it will have binary characters in it. It's also possible to store or transmit in the form of a PEM format. And this is an example here of PEM. So the advantage with this format is that it's stored in base64, and we have a header and a footer there, and we have the keys and the certificate encapsulated inside this form. This allows us to be able to send the keys in an email message or support them on a website. The DER format is a binary format, and in this case I've translated the binary format into hexadecimal. So each of these two characters is 1 byte, and what we find with DER is that we start with the 30 numbered there, and you'll find there are a few 30s if you go through the hex stream there. So that's the binary format, and that's the text format there, and we can translate between DER and PEM, typically using OpenSSL to be able to convert from the binary format into the text or the base64 format, and then vice versa again. And most systems will interpret either the DER format or the PEM format. So this shows an example here of me generating a key pair for RSA This is a 1024-bit RSA key or modulus. Okay, so we create a public key and a private key. The public key, if you're interested, is E, N, and the private key is D, N, where N is the modulus. The modulus is the multiplication of two 512-bit prime numbers in this case. Okay, the E value is defined there, and inside the private key we'll have the D value. So initially when we create it, we're creating it in terms of a PEM file. So we can see here is the PEM file. But then what we can do is that we can take the input, the PEM file, and we can output in the format of DER, and we get a format here of the DER file. You can see that when we list it, we get funny characters, which means that the file is in binary, or we can't really see the values there. But we can easily convert the binary, the bytes, into hexadecimal, and then we can interpret them. Then, once we've got the public and the private key together, we can extract purely the public key for distribution. So in this case, we'll take in the private key, and then we'll output the public key, and this is it here. And again, we have it in a PEM format. So we can see it's much smaller because it's only one key that's in there. It's only the public key, where the other one has got the public key pair, the two prime numbers, and the modulus, and so on. So our public key is a smaller one, and we can see here it's identified as public key, but this one is private. So we need to make sure that this one should never be seen in the wild. And then we can do again, we can take our private key, we can output our public key as a DER, and we can see here we have our binary format here. So how are we going to be able to read in this binary data for the DER? Well, we have what are called tags inside DER. So we just identify a few of them, and it'll give you the understanding of how DER is created and how we can actually interpret it. So normally the first thing that we see is the 30 hex tag, and that defines what's called a sequence, which then defines the next byte after that defines the length of the object that's going to be defined, and then the object itself. So it's a self-revealing format. The 30 then identifies the size then is read for the number of bytes, and so on. One of the most important elements is what's called the object identifier, and this is going to identify the crypto type, the crypto methods that's actually used. So the thing that happens after the 6 will define whether it's elliptic curve or RSA, say. And then a tag of 3 identifies a bit string coming up. So we have a tag of 3, we have the length of the bit string as the next byte, and then we'll have the bit string after it. So in this case we might have a sequence, we might have a size of that, we then have a 6 there, it defines the object ID, then we have another sequence, and then we could define the bit string, and so on. So we read the bytes from left to right, and we should be able to interpret them as we go along. So for the object ID, or the 6, if one of the elements of the object ID is to identify the types of keys that we're using. And it's defined in this dot format, which is a hierarchical format. So 1 is OSI, and then 2 is a member body, and 840 is the US. Then the value that we have after that defines the type of keys that we're actually using. So in this case, ANSI X962 relates to an elliptic curve method. And if we have a 2 here, it identifies the keys. these are keys that we're going to identify after this object. So other identifiers that we can have is an RSA certificate is identified with this one, an RSA signed signature is this one, and this one here is Diffie-Hellman. So in this case, here is a tag 606, and then we have 7 bytes after that to identify the key types. So it's 7 bytes long, 1 to 7 there. We can see there's the 1 and then there's the 2. It's not so easy to see the other parts because of the way that they're compressed, but we can use a Python program to be able to interpret that string to be able to get the object identifier. So in this case, we're using this one, which identifies we're using elliptic curve cryptography and not DSA or Diffie-Hellman. Another object identifier that we can get is the type of crypto, and in this case, we're using elliptic curve as an example. So this will identify the elliptic curve type. So it might be a 256-bit curve, such as P256, or a 192, and so on. Each of them have their own different characteristics, have their own base points and prime numbers and so on. So we need a way to be able to define that these keys and relate to, or these keys and signature relate to this type of method. So these are identifiers here. So it's the 3.1 identifies the curve type here for the curves, and then the digit at the end will identify the curve type that we have. So in this case we have a 06, we have 8 bytes now after it to identify it, and these 8 bytes, when we're interpreted, give us ECDSA, which is a signature type, and using P256, the NIST curve here. Okay, so in this way we can start to embed these types along with the keys so that they can be easily interpreted, or with the certificates. So here's a sample. These are some of the other codes that we can have if we're using different hashing methods. That's it there, and this is the methods this is the numbers that we identified before, but with different signature types. That is unique identifiers, object identifiers. Okay, so this is an example with the 03 tag, and we get to 03. We then get the length of the key in the number of bytes. That's 42 hex, which is 66 bytes. So 66 bytes, if we counted them after it, would identify the bit stream that we're going to have. In this case, we only need 64 bits, 64 bytes to give us 256 bits. So 2 of the bytes aren't actually used, and that's the 2 bytes at the start. With a public key, we normally have a 04 at the start of it, and then what follows is the x coordinate and the y coordinate, because with elliptic curve we have a base point and then we have our public key. Public key is a point on the curve, so we have an x point and we have a y point to identify our public key. Okay, obviously a private key would have a smaller size for that. Okay, so here's an example of a hexadecimal bit stream for our DARE format, and then we can break that down. We take it one step at a time. So that's 30 and then 59. We're going to be 91 bytes there, and then we see 30 and then a 13, which means that we now have an object which is 21 bytes long. 21 bytes, and that's the 7 and 8, and then the extra bytes for the 06 tags. So next we come across a 06 and a 07. So 06 is an object identifier. It's going to be 7 bytes to identify it. And this is the identifier here, which, as we've seen before, is that then we'll see a 006. If we go along, a 06 and then a 08, once we've interpreted that part. So the 06 and the 08, that identifies the elliptic curve type here. And then we can keep going along until we get to the 03, which is the next one here. So that's the object identifier in there. So then we have 03 and 42. They'll be 66 bytes long, so 03 and 42. So the rest of that there is now identifying the keys, or the public key for the X and the Y coordinate. So this part here is the start, and then we'll have 64 bytes of the X coordinate and 64 bytes of the Y coordinate to give us our keys here. Okay, so this is some Python coding here. So using PyCryptodom integration. So you can see initially we'll read in the string in there for this there, and then we identify the sequence objects with inside there, and we'll go around the loop identifying them. Each time we look at the start, the first byte or the first 2 hex characters, and identify if it's a sequence or if it's an object identifier or if it's a bit stream. From that we can then pick off each of the tags and interpret them. In this case, this is our object identifier decoder. We have a sequence decoder, and we can also have a bit stream decoder here. Okay, so this shows an example here of our stream. We hit a sequence initially, as we saw before. We hit another sequence from there, and then we can pick off, in this case there's the object identifiers in there, and then it eventually finds our public key in there. And then we can take it even further. If we've identified a public key, we can have a dir reader where we can input the key that we've found from we can input the key in the dir format into our Python program and display it, and then output in a PEM format. So in this case here, what we're doing is reinterpreting the key back just to make sure that it works okay. So in this case we'll read it in as if it's a P256 elliptic curve. We'll read it in and make sure that we can import the key correctly, because if it wasn't, then we would have problems. We can see it's an X and Y coordinate. If it was the wrong key for the wrong curve, then it would give us an exception there. So we can see here it works okay, so everything's fine. And then what we do is we can then output or export the key in a PEM format, and we can see that there. Okay, so let's see if we can get that to run. Okay, so this is our little program here. So we'll just load in a key. So let's see, we load in this one here, which is a 521-bit elliptic curve. And we can see here it's found that identifier, it's found that type, and hopefully that will relate to elliptic curve 521. Then we import the dir string here, this whole lot here, and then we'll put that back. We'll import that, and hopefully we'll get our key back there. And then what we do is we export that into a PEM format, and we'll get this one here. Okay, so that shows that that's working, hopefully. And if we want to try that out, then we can just run our little program in here, And there's the code that we have. Okay, so for certain types of curves, we check we can input the whole of the DER string. We convert it into bytes. We convert it into byte array. We take the string, hexadecimal string, and we convert it into bytes, and we can import that key into there and just check it. Then, as I said, we can then export that key into PEM format, so we can easily go between PEM and DER. So we'll just give that a little run just to see if it's running. Okay. So PyCryptosome is the method, is the Python library that we're using. So there's a string, there's the tags being identified, we import in there, and then everything is fine for that. Okay, so that's been a quick overview of PEM and the DER format. Okay, thank you.